Thank you so much. So I'm glad that we are speaking English because it was prepared in English, so it's a bit convenient. Here you can see a picture of me. Of course, this is very real from the theme I just did with my kids, bringing you some Kubernetes-related news, right? So a few words about me. My name is David Pech in Czech. I currently work for a company that is called Reich. And one of the things that is relevant to this presentation is that I am a golden kubestronaut from the CNCF. This is the company that is currently behind the Kubernetes and some other projects. And maybe just for you to understand, the company or the logic, how does it work, is that these open source projects are donated to the CNCF Foundation, which means that there is, let's say, some vendor neutral ground, so the Kubernetes could not be taken as a hostage as some other projects have been in the past. This golden kubestronaut title just means that I have a lot of time for some certifications and such. So why do we even bother in this particular year, this place, with something that starts with the K? When because I unfortunately use the Kubernetes word quite a lot, and sometimes when I start with it, I see those like angry faces looking back at me like, hey, there is some person saying that K word. It's almost like a swear word, something like this. But no worries, because what I'm basically trying to bring you here today is that you've already seen on the virtual machines, but now it's something brand new, much better, but the logic is completely the same as you have seen probably 10 years ago. So unfortunately, I would say that a lot of those features that the Kubernetes is getting is much more about aligning what we already had really 5-10 years ago. And even though there are some fancy fine-tuning around them, typically I would not say like that it is something like a game changer, and like definitely they are not of the value that the Kubernetes brought like to the market when it started. So first of all, let's discuss online pod resizing. You may have been in a situation where your pod did not have enough resources, right? Typically you have some monitoring to tell you that your pod might be running out of memory or CPU. So there is, currently it is in a beta. By the way, do you know what is the maturity level of the Kubernetes API, or should I maybe elaborate a bit? Would like anyone to elaborate on it? Perfect. So in Kubernetes, in order to be inside of the stable, I mean like version 1 API, this is the YAML definition, the first few lines that you have there, you need to go through several phases. There is alpha, which is of course alpha, some testing environment, some testing, let's say, a phase. Typically it can take 2 to maybe 4 Kubernetes versions to cross alpha. Typically you can expect some API, meaning YAML attributes changes all over the place, I would say. Alphas typically are something that you need to install to the cluster manually. It is not bundled inside of the Kubernetes. So typically those special interest groups that create Kubernetes will have some other pages where you can download this like special testing alpha features from. The beta, typically there are even multiple betas in those features. This can be turned on or off by default. This is, for example, on by default, meaning that when you install Kubernetes, even though it's beta, it should be already relevant. It is not advised to use in production, of course, up to some point, but you can feel it, you can try it, and you can verify if this works for you or maybe not. The graduation, of course, from the beta is to the stable later on. And there is also a discussion, as I mentioned, on versus off. So you will see later on some feature that is turned off by default. And this basically means that it is like slightly discouraged, or like the use cases that it is valid for are very narrow, I would say. So, but this is beneficial to everyone. The cap is the link to the Kubernetes enhanced proposal. This is a document that very well describes in depth like what is happening, what are the edge cases, etc. So you can go check it out if you like, but it's definitely like not needed. I have several examples of YAML, of course, because YAML is currently my main programming language, I would say, with Kubernetes that should be like super easy, so you get the gist. And we can discuss some edge cases or some more advanced topics later on. But I want you to like understand only the gist and have some notion that something like this exists in Kubernetes, and you are able to utilize it from the newer versions up to some point, maybe with some limitations. So this is what we are discussing currently. We have the limit set on the container, right? And if I change them, this requires a restart. I'm lying a bit, because you would probably not change it on the pod level, but on the deployment, etc. But let's pretend that you will change it directly on the pod. If I change it here, it would restart. If I would use the new features, I am able to select the behavior I would like to have. So either I can go with the old one, meaning that every change there requires a restart of those pods, or I can tell, hey, do not restart my pod. So why this is important, what's the benefit here? First of all, you can scale up your workloads, right? If you think about it, this sounds like very interesting, and the feature should have been there for years, right? But when you are maybe a bit like more staying on the ground, I would say that probably the thing you are concerned about is the memory limits. Because, CPU limits typically you don't care about. There are even some opinions that you should not set them at all, etc. The requests, once your pod is already running somewhere, are not relevant to you anymore because they are used only for the scheduling. So you really can benefit mostly from using and increasing the memory limit of the pod online. One small detail there that the Linux currently does not offer to scale down. So you can mostly scale up, and that's it. If you scale down, of course, this will trigger the original behavior, meaning that this will basically kill the pod, restart it. And also, there are some types of applications, such as Java, that has maybe some custom definition, how do they perform with the memory. So in Java, there is very different memory model than in Go, for example. So if you increase the memory on the container level, it basically doesn't mean it's a thing, because you need X and X, etc., and other parameters for the Java process itself to use the memory, typically. There are some edge cases, but typically you use these parameters in the production. So this is very nice. I guess that this should have been there for a long time, but it's kind of limited. The next candidate that we have is the pod level resource allocation. Again, it's in beta, and when I show a typical example of the problems that was introduced by Kubernetes, it didn't exist before, right? So we have one pod, and there are multiple containers inside of this pod. And we would like to we have maybe some company policy enforced by some Kyber or gatekeeper, etc., that we would like to set resources for every single container workload, right? So this is a typical dilemma that you have. You have your main workload, here some Postgres database, and then you have some auxiliary container. Here we use some exporter attached to it, but you can have something from your service mesh. It can be much more tricky because you may even have some workloads that automatically insert some of the sidecars, and you are not even aware of it inside your YAML, etc. And typically you need to set resources also there. But what would you like to set here, And especially if you have very different workloads, those like exported definitions look like this. There is one tricky thing about it, and this is the quality of service. So if the pod behavior from the scheduler perspective is different, when the Kubernetes will kill the pod is different, if you use the very same request equals to limits or not. And this applies to all the containers. So just if somebody, just a junior on your team will add this exporter, it will, behind the scenes, change the behavior of the pod, which is like completely invisible, not natural, but it's just by the definition that somebody is using different requests than limit on that exporter pod. So a slight improvement in the newer versions, you can define the resources one level above, not on the container level, but on the pod level itself, right? And this is what we've always wanted, and you don't need to care. So For any sidecar container, I would say it is typically beneficial. In theory, there could be some uneven containers, meaning that, for example, you have a pod consisting of two containers. One is very hungry at the pod start, then the utilization goes down while the other is growing up, etc. I have never seen such a behavior in my life, but officially it's there. It's definitely easier to understand, and there is that quality of service class, which is some intricate detail that you can now get correctly. Unfortunately, not all the features are following up yet. So, for example, a vertical pod autoscaler and others are not yet prepared. Maybe also your monitoring stack works on the container-based instead of the pod level based, etc. So, even though it seems like very natural change, I think it will take a lot of time to adjust to it in the end. Next up are the volume snapshot and volume group snapshots. When we've moved to Kubernetes, especially with any data-related workloads, we basically lost this feature, and I'm very glad that it's currently being brought back in. So this is basically the snapshotting of the volumes that you attach to your pod. The first one is a bit older, and it allows you to snapshot one individual volume. The second one is able to make several volumes at a time. So it is very similar to what you see in your cloud provider or your on-prem solution, etc., on the VM level. And basically, this is the technology, the underlying technology is completely the same. So we are getting the same snapshots that we had before. So it's just the cloning of the device that is somehow smart, and that should be much more performant. The group part is currently in beta, but I hope they will promote it soon. So the problem originally looked like this, or you had to do some custom copying of the files if you liked it from the pod through kubectl exec or some let's say nasty trick. A lot of people try to supplement this missing feature on the hardware level or on the storage level or on the cloud provider side, meaning that they try to do these snapshots somewhere outside of Kubernetes. But this was very challenging because it introduced a lot of overhead, and this typically meant that they need to have like their Terraform or whatever level they were managing their cloud provider infrastructure on in sync with Kubernetes. So for example, what is the benefit of this feature is that if you try to start a new pod, you can pre-populate the volumes from these snapshots as you would starting a virtual machine in the cloud provider's environment, the very same thing. So how does it look like? It should be very similar to this one. So there is a snapshot class name, which is the technology and basically I would say the driver that is providing the feature for you. You can even have maybe a different implementations of the driver because the snapshot class name is also some YAML defined somewhere, and there can be some additional parameters. So if you have, for example, I don't know, some different mechanisms how your storage provider can copy the data, it can offer it, and you can use multiple of them in the same cluster, which is very convenient. Again, this was a problem before. And you will basically say, hey, I want to have a snapshot of this PVC, and as the Kubernetes is a declarative language, now you input something like this, you just wait, and eventually you should get the result, very hopefully. No, I mean, this really typically works. I would not bother with it much. For the group, it's a bit different. You need to select a selector which matches your persistent volume claims. So you can have a bunch of them. They can be attached to the same pod or might not be. They can be even in multiple nodes, etc. Again, what is possible here depends heavily on the storage that you use. By default, like I would have no presumptions. I think that you need to verify everything here before it goes to production, at least. This is a table, why this is beneficial, but basically I'm trying to maybe like explain the snapshotting itself. So this is from the KubeCon Chicago, where one of the database vendor from Cloud Native PG was advocating for the change. And as you can see, the previous methods that were Kubernetes, not like Kubernetes native, but that were used in the wild were a bit different. And especially as we progressed to the larger, like multi-terabyte databases, they were not feasible at all. This snapshot recovery time is like significantly lower, and this is the basic gist of the idea what you get. Again, heavily depends on your storage provider, what numbers will be there on your infrastructure, how many IOPS do have provision, etc. But I think that the major like difference is obvious. This should be now the default for the database snapshotting and the database backup. Typically, I would not consider something else, especially if you are considering running databases in Kubernetes. Let's go over here directly. Let's use this technology because this is really the benefit that you will get from the newer versions, and also this is the way how you would do it outside of Kubernetes previously, maybe 10 years ago already. So the snapshotting itself is kind of quick, should guarantee point-in-time recovery, meaning that you will have the consistent volume backed up. This is not the same feature that you get from the lot of backup methods. If you just rsync the data, you are not guaranteed to have everything point in time recovered to that particular moment, etc. Recovery is kind of obvious, right? Very, very straightforward. What is an interesting use case is the cloning for the testing environment. So for example, if you are able to have a snapshot from production, take it on the development environment before clone it for each feature branch. This is, of course, very nice. Of course, if your storage provider is allowing not to copy the full extent of the PVC, but for example, the clones are shallow or so, again, you can maybe run 100 of your feature environments, not a big deal. Again, sorry, depending a lot on your provider of the storage. So now we progress to image volumes. This feature is kind of interesting because it has two very different, if you read the line out there, probably it's like not very beneficial, but this feature was very requested from two different worlds. First is the image creators, and maybe I will try to show you how does it look like. So imagine that you have some typically a large file. In this file, in this example, we are taking some of the models that we would like to incorporate to our application. And some people used to do it, or maybe still do it like here. So throughout the Docker file, they compose their application and combine their application together with the model they have. Typically, it looks something like this. You may swap the lines if you like. There are some downsides to it maybe. But you have typically a very large image that is being generated that is mostly the same because typically your application is like tiny next to the model that you are bringing. The second thing is that when you run it, it's very easy and it's not visible that there is some basically shared logic in between. You just, with this Docker file, you just run your application like this. The second use case that there is for the vendors of the images that really need to be very versatile. I have two examples from the database perspective. So the Cloud Native PG is advocating to have the image for the database very small, very light, but this typically means that there are not many Postgres extensions that are bundled in. And like, if you go to their GitHub, people like typically complain, hey, I'm missing my extension over there. And what does it mean? You need to create your own images, you need to maintain them, etc., even though the Postgres extension binary is typically the same for everyone. So we are missing some kind of like packaging on the image level. The other approach is from Stagres, which is another Postgres operator, and they say, hey, we would like to start fresh with everything at your disposal. So they have, on the contrary, very large images. Everything is bundled, but they need to care for it. You are not allowed to throw something away. Or again, you can maybe create your own images, throwing something away. But the other approach is maybe even harder as you get to that large language models and you would like to include 4 GB file to every image that you have, etc., and you cannot just slim it down. So the new Kubernetes versions basically allows a very simple thing. They allow you to have an image that is mounted into your main application. So you would typically, without this feature, you can typically imitate something like this through the indent containers, through some shared volume mounts, etc. But maybe this could be a slightly better approach now with the new Kubernetes versions. So you can see that we do have a single container here. We have a single volume mount to mount, and there is image reference together with image pool policy. That can also be the credentials. And what does it do? Nothing special. It basically downloads the large base image and places on that particular mount point. Not a big deal, right? But with this, you can really solve all those issues that I've talked about previously, and you can really have either your large file included, maybe some shared functionality included, or maybe you can use exactly the set of extensions that you would desire. You can, of course, have multiple of them. There are no limitations in this regard, as you like. One thing to note here is that, of course, like working with the mount points might be tricky, especially if you need to have them as files in the same folder, etc. So also Postgres, for example, from their end, they are enhancing the documentation, so you could define, hey, collect all these folders for the extensions, etc., etc. So it is not just the Kubernetes-related problem. It is that if you really would like to have multiple mount points, also the vendors need to adjust a bit. There is officially also the use case of limiting the bandwidth that you use. Personally, I don't have such an experience, but just to note, maybe if you are somewhere on the edge, if the bandwidth might be your problem, if you would like to reuse and cache those images, because one thing to note here is that the image pools are also being cached, and all the same infrastructure that you have in your container runtime applies to them. So instead of copying it all the time, it just pulls it once, or you can define the pull policy if you would like to have something else. No SWAP support. So from the start, we've been told in Kubernetes that there is no SWAP. However, things change a bit, but not quite, So this is, from the maturity perspective, this is the beta turned off by default, so you won't get it unless you opt in for it. There is an enhancement proposal for it, and there was a huge discussion if to even include this or not, because this is the state that we are currently in. Typically, we don't have SWAP. If we would like some, this is all that needs to be done. On the node level definition in the kubelet, you need to enable this feature, that's it. And if your application has some quality of service that is burstable, this means that you have a different request to limits. This typically allows your pod to utilize SWAP. There are no other definitions like on which node you can swap, what are the likelihood of not being attached to the one with the swap, etc. Nothing like this is done yet. There are some discussions on it, but basically you can utilize it if you like. So when or why does it matter typically? There are a lot of application types that typically are very hungry on the startup, and then once they are up and running, they typically decrease their usage of memory and such. Java is maybe, again, a good example. So typically they are very hungry on start. When they start, typically a lot of those classes are never used unless you do some optimizations on the build process, etc. So maybe this could be convenient for you. What does it basically mean? That you can save maybe some bucks on your cloud provider bill. You are in charge, definitely, if you would like to even to use it or not. If you use it, there is a performance penalty, as they always been. Some people are very contradictory to it, so this is the reasoning why it is off by default, because some people just don't like SWAP. Job success and failure policies. So probably you know that you can define something like cron jobs, right, inside of the Kubernetes. But especially if you run a fleet of them, it is kind of hard to work with them, have some common understanding if they succeeded at scale or maybe not. So this is what we typically had previously. There is just one single field that you can define on your favorite job, some backoff limit, meaning how many times the container can keep restarting. And now there is a slight enhancement, meaning that you can define policies which apply and how does they interact with the counting. So first of all, there is an action in the bottom that is called ignore. This means that you can define some conditions which are not being counted towards the backoff limit. So I am saying that my job can fail 5 times, right? It will retry it 5 times. But if the node is being disrupted, for example, I am running in AWS on the spot instances and that node goes down, this particular pod failure does not count towards the number 5. So especially, I think that like the spot instances or something similar is the major usage for this ignore. Really, probably nothing other that I would see in the field. The fail job can define basically that you might return some other return code from the process that could control how does it behave. So maybe there is some error that is really on the configuration level and it doesn't mean a thing to retry or so. So you can control it through this. And basically stop some reoccurrences from running and save again some instances. This is the other part of the proposals and other end, I would say. So this is for the success policy. So what does it mostly mean? You imagine that you are running some job in parallel. There are some machine learning workloads that you can run in parallel, and you just need a bunch of them to succeed. Other example is that you are running some time-sensitive workload, and it doesn't make sense until some time if the pods will succeed or not. So you can define something like this and say, okay, this whole job as an entity will be successful if only 8 of my 10 instances will succeed. I don't care about the 2, but still mark this job successful. Not sure if you are in that boat, but with some batch workloads, it could make sense, especially because a lot of those like business logic about the data transfers are typically in the way that you retry every 5 minutes or so. So maybe something like this might be convenient for you. Except from what I've mentioned, there is a very important term in the bottom here, which is called idempotency, meaning that no matter like how we try and how our system like designers try, we are of course not able to guarantee that our jobs are idempotent, meaning that they can run multiple times and produce the same results. They don't have any side effects, in other words. So I think that also like having these better policies is some kind of admitting that people are not able to do the best practices they should. It's just a real world, which is fine. And so we can provide them with some better tooling to accommodate for this failure and maybe not push them to have the idempotent services and tooling that they maybe don't control anymore, etc. The last thing I have here in this maybe already too long enumeration is the dynamic resource allocation. And basically what it is, you have some definition of the resources on your node that can be maybe shared, can be maybe used exclusively. What does it mean? The typical example here with the graphical cards or accelerator cards for the machine learning workloads. So imagine that you have on that particular node 2 very expensive performant GPUs, and you would like to dedicate like who can access them. I mean, which pod, in which parameters, etc. The DRR comes with multiple caps. It's a bit more complicated than this, but the main idea is described basically here. You define some special resources that are typically hardware bound on your node level, and then you can consume them on your pods. It can be in a way that, for example, the first GPU is being shared because, I don't know, the NVIDIA drivers allow you to share that accelerator card and you can run multiple workloads then in parallel, or they can be used completely exclusively. There can also be some definition how that GPU is being set up for that particular pod. So it has maybe some limitations or some technical details. Why this might be interesting? First, reuse, of course, of the hardware that you have. So graphical cards are the number one. You can also use network interface cards that are maybe a bit faster, etc. Or maybe you can use NVMe. So basically, anything that is super fast and you would like to get to the hardware level should come through this in the future. But in theory, you can even plug in your microphone and use it through the DRI and tell, OK, run my pod here on this particular node, utilizing this particular resource with this definition. Previously, you need to node pin, and there were some other nasty examples how to do it. This is much better, much structured, but it is more like aligning the pod, where it should run, how it should utilize those hardware resources. One maybe note what might come next, just maybe to mention the term that is called gang scheduling. So especially as your cluster gets larger, typically you would like to run the workloads that are related to each other very close, meaning that you would like to have 2 nodes for this particular group of 10 different pods because they interact in a certain way and they can benefit from the network locality, meaning that they run on that particular set of nodes and they have some benefit of the network latency, etc. So there might be some CRD in the future called pod group, but we will see. This is still discussed for alpha, again for machine learning. That's all I had. For everyone believe.